All right, and we are live. Let's see. Do we have anyone in chat already? Hello, hello. Welcome everyone. Hope you're having a wonderful Friday local time, whatever it may be for you. Hello, hello, Will. Hello, hello, Rick. Welcome. Welcome back to the stream. I saw your tweet, Rick. We shall see if I will struggle with it. If I will, then you'll see me struggle live and for the first time. I've not had a look at the challenge at all. So we'll see. We'll see how it goes. We've got another Will. Welcome. How many of you have already done the Advent of Code challenge today? How many are gonna try doing it while we do it live? All right. Will said he wrapped it up about an hour ago. Rick said I need to catch up on the last 5 days first. Actually, do I have to do all the previous challenges in order to do them? I don't think so, right? It's only part 1 and part 2 on each day that block each other, right? I'm not actually 100% sure anymore. Yeah, okay. I wouldn't be able to do all of them this year. All right, cool. Then let's switch over. As always, let me know if I can change anything about the background music or anything else. Just let me know. Otherwise, we'll get started right away. And of course, you can always tell me during the stream as well. But here we go. So, haven't even clicked on it, so let's see what happens. All right, so you're still riding a camel across desert island. I don't know what's up with that. I didn't look at the other challenges, but all right, we'll take it. When you spot a sandstorm quickly approaching, when you turn to warn the elf, she disappears before your eyes. To be fair, she said she had just finished warning you about ghosts a few minutes ago. One of the camel's pouches is labeled maps. Sure enough, it's full of documents, your puzzle input. How about how to navigate the desert? At least you're pretty sure that's what they are. One of the documents contains a list of left-right instructions, and the rest of the documents seem to describe some kind of network of labeled nodes. It seems like you're meant to use the left-right instructions to navigate the network. Perhaps if you have the camel follow the instructions, you can escape the haunted wasteland. After examining the maps for a bit, two nodes stick out, AAA and ZZZ. You feel like AAA is where you are now, and you have to follow the left-right instructions until you reach ZZZ. This format defines each node of the network individually. For example, okay, so is this like coordinates or what? Let's read onwards. This format defines nodes, each node of the network individually. For example, okay. starting with AAA, you need to look up the next element based on the next left-right instruction. Aha, okay, so if I go left, I end up in BBB. Okay. In this example, start with AAA and go right R by choosing the right element of AAA, CCC. Then L means to choose the left element of CCC, which would be ZZZ. By following the left-right instructions, you reach ZZZ in 2 steps. Of course, you might not find ZZZ right away. If you run out of left-right instructions, repeat the whole sequence of instructions as necessary. RL really means RL, 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 and so on. For example, here is a situation that takes 6 steps to reach ZZZ. Because L, or no, I don't understand this. Of course, you might not find it. If you run out of left-right instructions, repeat the whole sequence of instructions as necessary. Hello, hello, Nicholas. Okay, I think is this just a different, whoops, is this meant to be a different set of nodes? And so if I go left, left, right, I think, okay, so if you run out of left-right instructions, repeat the whole sequence of instructions as necessary. So it takes 6 steps because LLR does left, so we end up in BBB, then left, we end up in AAA, then right, we end up in BBB, left, we end up in AAA, left, we end up in BBB, and right, we end up in ZZZ. That's why it takes 6 steps to reach ZZZ with this constellation of nodes in the network. That's how I'm understanding this. So starting at AAA, follow the left-right instructions. How many steps are required to reach ZZZ? Okay, so to begin, let's get our puzzle. Okay, so let's download this, or no, actually let's copy this. Okay, so, and let me know if I can ever make any of this any larger. So we've got our input. And we'll just, yeah, we'll make this very naive. All right, so we've got that. All right, so we will start with defining our data structure. we'll have node that has left node, right node. And is that how we want to do it? Let's see. We could also have, hold up. Whoops. Okay, so we do have to start with that. Did we need to find AAA first? Okay. Okay, so we can have our network as well. Start. And then we'll do load network. I'm just gonna do all of this in memory and basically just I think I'm gonna make this really easy for a start. Just have nodes. Just keeping it easy for a start. Maybe we'll optimize this later. We'll see. All right, so we'll have some sort of input. Let's just make this a reader, and we'll say that this is a scanner. Maybe we'll even just call this load. And then we'll have our network. And we'll get our instructions. We'll make this integer and left, right. And then we'll say, yeah, exactly that. All right, so we want our first line, instructions line. If then we want an empty line. And from now on. All right, so from here on, we now are gonna parse. Oops. Hello. Okay, we're gonna make this easy and kind of unsafe. We're just gonna split by this. Actually, we're gonna split by this. And then remove the trailing and then split by this. Keeping it easy for us. All right, so we'll ignore to do instructions. We'll do the instructions later, and then for now we'll scan our nodes. So we are going to, yeah, of course, we'll need our line. And like I said, we are going to split node based on, forgot to copy it. Parts. Unexpected EOF. Not really. I'm just gonna do invalid node line. Will was asking if I can move the camera location. Hard to see the code. Maybe where do you think it would be better? Over here? Is over here better, maybe? Is over here better? Let me know. I'm guessing up here is probably gonna be better. Okay, awesome. Alrighty, so actually let's extract this real quick. So we're gonna parse node line. We have our line, that's a string, and we get a node back. Yep, that looks about right. And then we actually want the name of the node as well. And this is actually not quite correct, but we'll get there. Node name, node area. Okay, you say. All right. Bottom left it is. Alrighty. Let's then. Yep, and we want to then add network node's name, and we add the node. Yep, that looks correct. But this is not quite done yet. Let's look at this format again. Okay, so if it doesn't end in close parentheses, let's fix that. If does not have suffix, yeah, that looks correct. And now we want to split by left, right, left, right, parts, and this. Again, if the left, right parts are not 2, then we do that. And with that, I think we've got everything. Parts 0 is our name, and then our node is left, right, parts, left, right, parts. All right. This is already super obvious. Later, if we do some profiling, this is very, very likely going to show up, especially this string splitting. It's much better to kind of first find the index and then work directly on the string so that we don't keep doing allocations, because string split does actually multiple, actually no, it does one allocation, which is, if we can already look at it, within gen splits, it does this allocation, which is usually pretty expensive if it is in a hot loop, which I assume, you know, in this particular example, it's probably going to be. Although we'll see, you know, whether the pathfinding is going to dominate, but we'll see. All right. So. Yeah, I think that's it. Now we want to scan the instructions line. Parse instructions string, and we're gonna get that correct. Okay. Okay. Instructions. I'm just gonna errors, parse instructions, error, we return that. We'll be nice and say build a nice stack. Let's do that here as well. Now, what we're gonna do is we're gonna actually do a quick. We'll pre-allocate this. So inserts make, yep, exactly like this. I guess I'm gonna be nicer to do it like this, and then we'll do. Yeah, that's exactly what I wanted to do. Range over the line, and we can do. Yeah. Is a switch case good here? Yeah, I guess it's fine. Is that what I called them here? Yeah, okay. That looks good. All right, cool. Yeah, that looks all good. So now I think we've got everything. I guess if we loaded all of this into memory, we could make this, and if we just operated on the byte slice directly, we could definitely make this a lot faster. That always depends on whether we can actually hold all of this data in memory. Oftentimes, if we do, you know, interesting things, maybe it just doesn't fit into memory. But For now, we'll assume that it will. All right, so write a couple of tests. We wanted to parse instructions. Let's paste this. What is that? So LLRLR. All right, and now our expectation is left, and so on. Let's see if Copilot did it correctly here. So left, right, right, left, right, right, right. Okay, that looks correct. Okay, so now test cases and parse instructions. Yep. That looks good. All right, test. Mod init ID test. Okay, so we've got a couple of things to fix. 40. Whoops. What was it complaining? It's declared but not used. Okay, we need to, of course, return. I guess we can. All right, now 67. All right. Now 97. 19. What is it saying? I don't know, test. Okay. Okay, so that's looking good. Now let's what was the other thing? Parse node line. And yeah, we'll just have a pretty similar test setup. Our expectation is let's just define an inline structure, I guess. Node name and a node. Let's do, oops, do this. Now we'll do A equals. Right, let's start with that. It's not used yet, of course. Parse line node. What did I call it? Other way around. All right, so here we go. It returns 3, of course. So the node name, node, and there. Okay. So not the length, just the node name is expected node name. And this we won't look at the array, but we will look at this. Okay. Okay, so what? Okay, so we looks like we didn't get it quite right. So expected BBCC, yeah, that's exactly what we expected, but got AA. Okay, let's look. So we've got our part. If the second part doesn't have that, okay. Okay, so here's the first thing we need to make. Yeah, we need to trim the closing parentheses, then the left right parts. Here's the mistake. We don't want to split line, but we want to split part 1. All right. That looks better now. Tests passing. And now we want to actually load and then actually run our instructions. Okay, so our main, we load. All right, that's fine. Maybe we'll do a slightly better thing. Do a log fatal. Okay, our input is input, and we just pass in f. That, and before closing it. Now we have our network, and we repeat our instructions infinitely until we're at the end, until we get to ZZZ. So okay. Anyway, so we current is n.nodes AAA. Now we based on our instruction, left or right, we make this move, and if if current dot left equals zzz, then we are done. Okay, we're gonna want to and what do we want to return? What is the result? How many steps are required to reach? Okay, so step count. We do step count plus plus here. And we'll move this to a function in a second. Yeah, we do the same thing, and I suppose actually yeah, no, I'm okay with this. I don't care about a tiny bit of duplication here. Okay, so what do we call it? Run? I don't know. Network and instructions. I don't care what it generated there. I'm gonna. Yeah. Anyway, I'm gonna take this. Maybe it's identical. Okay, it's identical already. And then otherwise return. This is unreachable. This is unreachable. This is fine. Okay. We've got that, and now we do that. Okay. I think that's it. Let's see. Assignment. Okay. Load here. Oh. Nodes. That. Run. Go. All right. Looks like 1,419. Maybe that's correct. Maybe it's not. We shall see. That is not the right answer. Your answer is too low. If you're stuck, make sure you're using the full input data. There are also some general tips on the About page. Okay, so where did we go wrong? We are too low. What did it say? Your answer, if you're stuck, make sure you're using the full input data. I mean, let's just quickly check. So there's 2 lines that are not nodes. Let's just double check that we have the right amount of nodes. So let's, I suppose we'll end up writing a test for this anyway. Whenever we get the correct answer, we'll. And for now, we want to make sure if run is equal. What did we get before? Oops, here. Actually, I want to do t.payTime. No. Did not expect. Count error run instructions. No, we don't need to count at all. Okay, and what is going on here? Run. Oh, it doesn't have. Okay, weird. Okay, I don't know what I did wrong before. Okay, so I guess we don't really need our main function anymore. And now what we're going to do is we are going to ensure that if length of instructions is not some number that we'll find out in a second, then total expected instruction count. Again, we'll find out in a second what it's actually supposed to be. Okay, so just checking. All right, got 277. Now we'll do a word count, count the number of lines in this input file. And oh, interesting, indeed, 788. Okay, so we want 786, I suppose, since the first 2 lines in the input, the first one is the instructions, the second one is an empty line, and then we have, yeah, 788. Interesting. How come we stopped early? Or what happened? Are there duplicates, maybe? Let's see. Oh, let me open this way. So our run looks okay. Loading. Okay. Now we scan a line. Let's just line scanned. Let's do something quick and dirty. And we'll just do this. Line scanned to see if we're exiting early, which doesn't look like it. Otherwise, we should get an error. So there seems to be something about this. I don't know yet what is going on. Okay, so that looks correct. So that is not an issue. Let's remove that. All right. So nodes. Parsing looks right as well, and our test also says that it's correct. So it seems like, let's have a look. Duplicate node. Let's see if that... No duplicate node. Let's see. We do scan each line. We do not have duplicates. Let's have another look at our input. How about... Okay, let's do something a little different first. Let's not do this. Let's... let's give this a name. Let's do that then. And we'll we'll just have a nodes array. And we'll just do append to this. And yeah, we'll just kind of return. I guess I still like the idea of encapsulating this, but our network will just have a list of nodes. So network. Now, I guess then maybe what we can do is we can bind this to N. And we'll add a find function as well. Network. This is going to be awfully inefficient, but we'll bear with it for a second. So now we do n.find and not found. We'll, I guess, what did we? No, we never did that. We'll do we'll just return -1 for now. Okay, so we need to do the same thing everywhere then, of course. No. All right. Then here as well, found one, that, and we'll do find here again. Okay. And that's fine. Okay. All right. All right. Now, okay, 79. Okay, I guess we'll just do that. Now 110. Just oh. And then in main test, undefined run. Oh yeah, okay. Because it is end of run. And 84. I guess we can do justice then. And we can remove this, and we can remove that. Oops. And expected is just node. Oops. Like that and name that. Okay. Now let's see. Expected. All right. So let's see if that. Okay, now we got 277 instructions. Wait, what? Oh wait, wait, instructions? I think we might have made a mistake in our instructions. Yeah, no. The it's the node count expected. Node count. End of nodes expected. But we should probably count the number of instructions as well. Expected node count and end of node. Okay. But we are still getting that number of steps. Wait, but so that means that we do get that amount of nodes, but let's see, expected instructions count. Instructions, yeah, expected some. Oh, wait, this is not instructions. It's nodes. Got that. Okay, now let's see. Rick is saying, I think it's time to get a green screen. Actually, as Polar Signals, we have already purchased a green screen. I think it's at Matthias's house though. So maybe I can grab it one of these days. Good suggestion. All right. I'll move this up a bit. Now, let's see. So we got 277 instructions. That might be correct. All right. Now you can see my terminal output. Let's move myself up here for a second. So what I want to do is I want to just get the first line of the input. And I want to do a word count for characters 278, which seems correct because I think it counts the line break as well. Yeah. Okay. So 277 is correct here. No. But we determined that 1419 is not correct. What are we doing wrong? Let me move my head back. Okay. Interesting. It said that our solution is too low, right? That is not the right answer. Your answer is too low. Let's take the smaller example and write a test for that. Yeah, I'll just write it on separate test for this. So test run small. So we'll just do the buffer. Something like this. Let's go back. Okay, so load binds the new reader, and we expect 1, 2, 3, 4, 5, 6, 7. Oops. Nodes, and we have 2 instructions, and we said that in this case you reach ZZZ in 2 steps. If it's not 2. Okay, so this one passes. Now, while I'm writing this test, maybe let me move myself. Oops. Over here again. Okay, let's write another test. Maybe we'll do some test cases here. Input, we'll have our expected node count. We'll have our step count. Oh no, and expected instruction. Expected instructions. Our expected node count, no, 7. Our expected instructions count is 2. Okay, so now for test case, that. What's going on? Comma. Are we missing? Yeah. And it's input. See that input. Okay, so now test case, test case, case, test case, and okay, so that's still going through. Let's just double check that everything is working as expected. Okay, and here as well. Okay. All right, then let's copy this and we'll use our next known example, which is this. Okay. Expected 7 nodes, got 3. No, that's correct. Expected 2 instructions, got 3. Yeah. Expected 2, got 3. That's not right. Wait. No, we want 6. Okay, so here is probably our mistake then. Okay, so what happened? We start with A. We for loop. We go with L. We are at B. We go to the next one. Our current is so the question in chat is, I switched tabs for a minute. Are you properly looping around when you exhaust the instructions without reaching the destination? Yeah, this is probably what's not going right at the moment. I thought we were, but it looks like that is not the case. So that's what this test basically showed us. It's saying that the code is saying that we are done with 3, but that is clearly not correct. So why is that? When we're done with our instructions, we just, whoops, we just go for it again. We don't stop. We just go for it again. What am I doing wrong? We are not at the end. All right, so let's see. Let's print the current name. Actually, let's give these two tests also names. Sample and wrap. Make this, yeah, exactly that. Here we go. Run. So it says AAA, BB, AAA. That doesn't seem right. So AAA, we go left. BBB, we go left. So we are at AAA. That's correct. But now we should. Why do we return? Let's also print our current step count. Yeah, that seems right. Oh, hold on a second. We set current and then check current left. That's not right. That's not right. We should just check if current name is CZZ, we return step count. And if not, we count up and do a step. Wow. Okay. Okay, that looks better. Now let's remove this print line. Okay, and what is our result for the first test then? Okay, that is much higher. Oh gosh, okay, wow. That took much longer than I expected. Okay, so there you go. Very easy to put in a bug there. That's the right answer. You are 1 gold star closer to restoring snow operation. So before we continue, I'm gonna just quickly add this count to be our test. Then that, yep. And tests are passing. All right. Okay, cool. So let's go back and have a look at part 2. All right. So part 2, the sandstorm is upon you and you aren't any closer to escaping the wasteland. You had the camel follow the instructions, but you barely left your starting position. It's going to take significantly more steps to escape. What if the map isn't for people? What if the map is for ghosts? Are ghosts even bound by the laws of space-time? Only one way to find out. After examining the maps a bit longer, your attention is drawn to a curious fact. The number of nodes with names ending in A is equal to the number ending in Z. If you were a ghost, you'd probably just start every node that ends with A and follow all the paths with the same time until they all simultaneously end up at nodes with Z. For example, LR. One B XXX. 1 B XXX. 1 Z. Okay. Here there are 2 starting nodes, 1 A and 2 A, because they both end with A. As you follow each left-right instruction, use that instruction to simultaneously navigate away from both nodes you're currently on. Repeat this process until all of the nodes you're currently on end with Z. If only some of the nodes you're on end with Z, they act like any other node and you continue as normal. In this example, you would proceed as follows. You are at 1 A and 2 A. 1 step. You choose all of the left paths, leading you to 1 B and 2 B. You choose all the right paths, leading you to 1 Z and 2 C. You choose all the left paths. Wait, why did we choose? So all the left paths, that's because of this. So that leads us to that. And from 2 A, that leads us to that. Okay, that makes sense. Then you choose all of the right paths, leading us to, let's start with this one, then 1 Z, yes, and on 2 B we are going to 2 C. Okay, I guess anyways. And then you choose all the left paths leading you to 1 B because we were on 1 Z. And 2 Z because 2 C did that. Okay. Sorry, the left path. You choose all of the right paths leading you to 1 Z and 2 B. Okay. Wait, that's because why? We were on 1B. Okay, yeah. And so we're going to 11Z, and we were on 22Z. Taking the right path, so we're going to 22B. Choose all the left paths leading. Okay, okay. Aha. Okay, so both need to end in Z. Okay, now I get it. All right, so simultaneously start on every node that ends with A. How many steps does it take before you're only on nodes that end with Z? Okay, so before we do anything else, just like last time, let's make sure we commit this. Day 8, part 1. Now, just like last time, copy part 1 over to part 2. And no. Basically, all we do is find the current, and we do that by looping over our nodes. And nodes, and then if has string dot has suffix and dot name A, then add this, and then the instructions continue to be the same. So what we want is we want to apply the instructions for every current. So how are we gonna do this? I guess we for loop over all the currents. And if does not have the suffix z. What am I doing? Then we break Um, all end in Z. And if all end in Z, we return the step count. Okay, that and the currents I. Okay, fine, we'll do var found bool. Okay, I think do we have an endless loop or is it just very slow? All right, probably an endless loop. Okay, let's go back again and try some smaller examples. Yeah, let's do our smaller examples again first. So what did we have here? We want 6. We'll remove this one. Oops. We got 8. Why did we get 8? Wait, what did we get 8 of? Nodes. Yes, that's correct. 8 nodes is correct. Oh. Expected 2 got 6. That's probably just the wrong expectation. Let's count, right? 81. Oh, wait, 81. Oh, yeah. Okay, expected step count 2 got 6, and 6 is indeed what we wanted, so that's correct. So maybe it's just very, very, very slow. Which could be true. Our search is extremely slow. I guess let's leave this running for some longer then. So this one did terminate. I wonder, let me output a CPU profile already and do a timeout of, let's say 30 seconds. That probably is gonna actually time out, but I'm not actually 100% sure if the profile is written if we time out. That would be an interesting one to try, but it would actually be a nice opportunity to try our profiler. Let's see though. Is that non-empty? It is non-empty. Okay, that's cool. So let's upload that then. So yeah, as expected, that is spending a very large amount of time in find. Okay, so that means we want to store this some different way. How do we do that? Okay, so I think the fastest thing that I can think of is essentially a prefix tree. So because all of our node names look like, you know, 3 letters, what we can do essentially is have a tree that at each level can have its prefix, so or has one character, and then at depth 3 we would have an integer into our node array. So what would that be? So prefix tree node let's do it this way. That has so we have A to Z. How many letters are in the alphabet again? 24, 25, 26, something like that. Anyway, we need number of letters in the alphabet. Let's just Google this real quick. Number of letters in the alphabet. Just want to get this right. 26 letters. Yeah, okay. All right. So we have 26, and that's integers. Oops. Yeah. And then we have a prefix tree internal node. that then has nodes, just like that. Yes. All right. So then we, after loading, over here, we build prefix tree from nodes. So we need a root indeed. And let's see. Yeah, we'll just make this really dumb, and we'll just do static 3 levels. In this case, that's okay. How did I define it? Okay. Okay. So I'll just loop over all the nodes, and I will loop insert node to prefix tree. And now name. Yes, we want to do for each of the characters in the name. Yep. Okay, fine. We can do an area. That's fine. And yeah, exactly. Yep. If it's not there, then we do that. And then if it is there, yeah, and then we grab that. And if we are at the end, we have reached our current. No, actually, we only want to do actually, we're just gonna make this a little easier and just do leaves. This could certainly be optimized for the amount of memory that it uses, but this just makes it easier. Now we've kind of arrived at and so we then want to choose the last character. That's char. We'll just validate it real quick as well. And then no, we wanna set index the index like this. All right, I think. All right, thanks for stopping by, Rick. Alrighty, so now we've inserted it into the leaf, and I guess we can wrap this into a nicer fix tree so that we can define the search function on this. And I guess we'll panic here if this happens. Okay, so we actually need to what is this now here, and now we want to define a find function on the tree. Do it this way. Tree find main string. And we'll, for each character, search. Let's just quickly check that the character is, yeah, panic if it's not. What did that generate? And what did we want to return? We would return our integer. And here we would return, again, we would want to do one less. And then, hold up, the insertion. Oh, no, this is correct, yeah. And so the last step is then that, yeah, we do this and we return that. And so now our network can have the tree as well, which is a here. And over here, we're gonna do, oh, that is a good idea. But I meant to do our tree. I thought we were, no, okay. Let's do that here already. Okay, so now we build prefix tree node from nodes. And now we'll do nodes and T3. And now we can replace our find function with, we'll find our index, and then index is -1, we return node false, and otherwise we'll return that. All right, that looks good. See? I suppose there's still a chance that we have an endless loop. Okay. Let's check if our small example. Oh, okay. Invalid node name. Ah, okay. So we can have numbers as well. I forgot about that. It's a 11A. What? Uh-huh. Okay, then. Interesting. The input data doesn't have that though. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. I guess that's fine then. Let's have another look at the profiling data. Okay. It's all in finding. Now the question is, do we just have an endless loop? Or are we just not waiting for long enough? I'm just gonna, in a separate window, just keep it running for a while. See what happens. So our unit tests are telling, or our unit tests aren't really telling us anything because we wrote the prefix tree in a way that it doesn't work. In the ASCII table is, I always forget this, is the numbers before. Oh. Okay. Yes, numbers are first. Okay. We could expand it, of course, but let's see if there's... Nope, it's still running. Then let's try to fix that. We will... We'll do a quick function char to index. No, if... No, that's not what I want. If character is larger to A and yeah, then we'll do 10 plus this. If it's something between that, yeah, then we'll do that. So basically what we'll do is 0 to 9 is to 0 to 9. So we'll have 36 instead of 26 indices. And if this happens, we're fine. Okay, we're gonna want it. We already have an index variable. Okay, we'll use room. Huh. Oh, did we accidentally override this index previously? That's very possible. Pretty sure it's not gonna take that long. Okay, no. Got our prefix tree. Double check this find function. Yeah, we need to move this up on us. Okay, yeah, that makes sense. Now have 36 here, 36 here, and try to run this again. Hmm. Again, I'm pretty sure it won't be that long, but let's just do that again. Oops. All right, then in that case, let's no, yet no, our smaller example should work, right? Okay, this works as expected. Oh, okay. Oh well, this okay, timed out. Let's just see if this is any different. It doesn't look like it. Here we go. No, it looks exactly the same. Let's check that we select starting node correctly. Okay. So if the node has the suffix a, again, let's leave this running some longer then. Although this should only make it slower than before. Because in the profiling data, we could see that the char to index was now pretty significant. So for all currents, running. Let's extract starting nodes for a second. Okay, so currents by starting node. So let's quickly write a test for this. Expected starting nodes. Count and dot starting. Okay, so let's just quickly run this on our small example, and then we'll run it on our large example as well. Oh. Okay. So starting node count. I don't know. Let's say 2. So and now we do got 6 starting nodes. Let's see. Input, grab, and we can do something like dot a, and it starts with, yeah, that's 6. All right. Oops, so open. I don't know if the other pack. Yeah. Is there a different input? No. Are there cyclical things? That's cyclical. Hmm. Now the question is, have I broken it with the prefix tree, or the other test suggests no, but of course that's a possibility now. Hmm. All right. Unfortunately, I actually have to run, so I'm gonna try. Maybe I'm gonna go back to this later, but this is all the time I had for today. So that's it for today. Maybe I'll still be able to finish this and solve this later, but that's what we got to do, had managed to do within this time. Unfortunately, we didn't really get to do much profiling today, although, of course, the prefix tree is certainly going to be much faster than a linear scan over our list, but of course, doesn't really help when it's not solved. So yeah, that's how it goes. Sometimes we win, sometimes we lose. All right, thanks for tuning in, everyone, and happy profiling. Thank you. Bye-bye.